the problem statement is count the number of primes less than a non-negative number n. So thanks to the internet, I learned about the sieve of Eratosthenes, and apparently it's a very efficient way to just finding primes. Essentially, it's just you have a list of normal numbers of like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so 10, 11, and 12. Okay, so I'll be working with these numbers. So how it kind of works is it's just I'll be marking these numbers whether or not it's a prime. So like 0, it's not considered prime, so this will be false. 1 is also not a prime, so it's considered false. 2 is a prime, so that should be considered true. 3 is a prime. 4 is not because it's divisible by 2. And prime, not prime, prime, not prime, not prime, not prime, prime, not prime. So like I'll be marking these. So it looks like it's just a list of true and false. So that's what I'll be doing. How the method works with the sieve of Eratosthenes is that it kind of looks for the squares, and of course a square by definition is not a prime, and I'll be looking for every step. Like for example, if I'm looking for 3 is a prime, but 3 squared 9 is not a prime because, well, divisible by 3, and and every 3 numbers after that is divisible by 3. So like for example 9 and then 12 and then 15, they're all divisible by 3. So that's how it's going to be marking. So how it works is I'll be making a whole list of all trues of like however many numbers. Like for example 10 numbers, so I'll have a list of 10 numbers starting at 0. So 0, 1, 2, 4, 5, 6, 7, 8, 9, 10. So, oh wait, no. If n is 10, then that means I have 10 numbers. Then it's just 0 through 9. Those are my 10 numbers. And since I'm working with a list, there's a good reason why I'm starting at 0, so that I can just use straight up the index. So I'll be making them all, well, to start off with the problem, I'll be making them all true first, and then the method will go on into marking these true using the sieve of Eratosthenes. So how it works is like while the number I'll be starting with is always at 2, so if p squared is less than the given number, like n, then well, let's make sure I increase p. Always like to make sure I have an end result, so given n, p. Alright, now in between it'll be another loop starting at the square. So it'll be for p times p. Oh no, for I in range starting at p squared. Starting at p squared all the way to n, the given number n. And the step I'll be taking every time will be p itself. Like if it's 2, p squared is 4, and then every step I'll be taking is 2 because p was 2. So It'll be 4, 6, 8, so on and so forth, and I'll be marking them all false, as in they're obviously not primes. So that's how I'll be approaching it. And in the list, let's just call it a list of I, and then I'll just set it to false. And essentially, in the end, I will have a list of true and falses where every true will be on the index of a prime number, and then that's how I'll be finding the primes. And in order for me to count it, I don't need another loop to count it. I can just use some kind of counter starting at 2 to mark, because I already know 0 and 1 are not primes, so I'll start the counter at 2. And to avoid repeats, and if a list of I is true, then I'm going to go counter plus equal 1. And I kind of didn't explain what this counter is going to do, but essentially is I have an entire list of numbers, so I can just need to look at the length of a list minus the counter that I have, and that should equal to the number of primes. Initially, I did, after I had my list of true and falses, I did use a for loop to count until I realized, like, wait, I could just subtract instead of using a whole method of just counting every single true. I can just find all the non primes, count all the false, and then just subtract by the length of the entire list, which is, I believe, is way better than having an entire for loop. And that's essentially what this does. That's how the sieve works, and apparently it's the most efficient way.